Okay, this segment is going to deal with Coulomb's law and its impact on electrical forces. The person given credit for coming up with the relationship is Charles d'Augustin Coulomb, who's shown there on the right, back in the 1700s in France. Coulomb's law, in words, is stated as the electrical force between any two objects is directly proportional to the product of their charges. Now that means we're going to multiply the charges by each other, and then inversely proportional to the square of the center to center distance between them. So that means their center to center distance has to be squared. So it has a large impact on the effect. And being that it's inverse, it's going to make, as the distance goes up, the force is going to go down. Okay, this is what it looks like in terms of symbols. The force, F, that's the electrical force, is equal to K, that's the electric force constant, which is 9 billion, 9 times 10 to the ninth newtons for every meter squared and coulomb squared of distance and charge. Q is the symbol we use for charge, so Q1 times Q2, charge 1 times charge 2, over the distance to squared, and again that's center to center distance. So if you have 2-point charges, it would be the center to center distance between them squared, and then their amount of charge, Q1 and Q2. You would multiply the two charges and divide by their distance squared between them, center to center, and you have to multiply it by this constant K, which is the basic electrical force constant. Okay, so here's an example of using Coulomb's law to calculate something. In this case, we're going to determine the magnitude and magnitude of the electrical force between two objects, two balloons. So the balloons are charged. We're assuming the charge is all acting at the center. Now in reality, the charge would be on the surface, but we're going to measure the distance from the center of each of our objects. They have an equal amount of charge. Now one of the things about charge is measured in coulombs after Charles Augustin Coulomb, and the symbol for that is capital C. But it's very, very difficult to get one coulomb of charge together because the like forces, the like charges try to repel. So most often you will see charges in the amounts of NC or mu C. Now N stands for nano, and it means times 10 to the minus ninth. And the Greek letter mu stands for micro, and that's times 10 to the minus 6. So we'll see how that comes into play as we do this problem. The charges on each of these, this is Q1, is negative 6.25 nanocoulombs, and this is Q2, which is negative 6.25 nanocoulombs. The separation distance between the two actual charges, center to center, is 61.7 centimeters. And we want to calculate F, the electrical force. So we're going to use Coulomb's law, but there are a couple of things we have to be careful about. Again, NC stands for nanocoulombs. So when I put that into the equation, I need to use times 10 to the minus ninth. And then centimeters will not match up with the constant, so I need to put that into meters. So the electrical force is going to be equal to K, so that's 9 times 10 to the ninth, and that's Newton meters squared over Coulomb squared, multiplied by negative 6.25 times 10 to the minus ninth coulombs, and then you multiply by itself again, negative 6.25 times 10 to the minus ninth coulombs. In this case, we multiply by itself because both the charges are the same. If the two charges are different, you'd multiply the two different charges. Now, 61.7 centimeters would not cancel with the meters here in the constant. So I need to change this into meters. So centi means 1/100th. So it also means times 10 to the minus 2. So I'm going to move the decimal place 2 times to the left, or divide by 100. And that's 0.617. And that's meters, and that's squared. Since it's meters squared, those meters will cancel with this. Coulombs will cancel here with the square as well. And our force, like any other force, will be in newtons. From there, it's just a matter of calculating it and getting a number. And when we do, we'll think about that in terms of how it compares to gravity. Okay, when I calculate that out, I get an electrical force of 9.23 times 10 to the minus 7th. It's a force. All the other things cancel out, so it's newtons. Now, that's a small number, but you can see I have very tiny charges, and I still managed to get a halfway decent amount of force. And that's because electrical forces are much, much stronger than gravitational forces, as we'll look at here in a bit. Okay, another example problem. We have two balloons again, but this time they're different charges, and we have the force this time. We're trying to figure out the distance between them. So this same basic formula, but we're going to do a little bit of algebra to solve it. So the force is 0.0626 newtons. That's equal to K, 9 times 10 to the 9th newtons, meters squared over Coulomb squared, times positive 3.37 times 10. Now micro here, this Greek letter mu stands for times 10 to the minus 6. Okay. Times negative 8.21 times 10 to the minus 6 coulombs. Now we don't know the distance, but we're going to put the distance squared in here. Now we can go through the numbers and calculate, and we've got to get this distance by itself. Now in this case, all I really have to do is multiply both sides by distance squared, and then divide by 0.0626 newtons. That'll get rid of that, and put that over here. And now I can run the numbers and get a value for the distance. Okay, with doing that, I get distance squared equals 3.98, and that will be in meters because the newtons here will cancel, and these coulombs squared here will cancel with the coulombs from the two charges. So that's going to be in meters squared. Now that's distance squared. Now that's really close to 4, and the square root of 4 is 2. Now it does actually come out to be negative, but the negative really only tells me the fact that these two are opposites and they're going to attract. So I'm not going to worry about the negative sign when I'm trying to calculate this distance. It's just the square root of 4 essentially, which is going to be 2 meters. Meters squared is square root of meter squared is meters. So we've placed them just about 2 meters apart. So simple enough calculation, does involve a little bit of algebra. Do have to be careful about your units. Make sure you know what micro and nano mean. Now just to finish up quickly here, the two main forces we're looking at right now are electricity and gravity. They both are very, very similar. They're both based on fundamental properties of matter. Electricity is built on the fundamental property of charge. And again, every electron in the universe comes with its own little charge of negative 1.6 times 10 to the minus 19th coulombs. Coulomb, again, is unit of charge. And then gravitational forces are based on mass. Okay, and that'll be mass in kilograms. Now, any atom has both charge and mass, and therefore they're fundamental. You can't get away from them. Everything has it. And they have the same inverse square nature. 1 over distance squared. Two of the biggest differences are this K is a very, very large number, and therefore electrical forces tend to be very, very strong for small charges. G, big G, the universal gravitational constant, same everywhere, is actually a very small number, very, very small. Therefore, to get a significant amount of gravitational force, you need really big masses. So this is a much weaker force than electricity. A second really important fundamental difference is, as far as we know, gravity can only pull. So this can only attract, whereas electrical forces can, depending on the type of charge you have, since we have two different flavors of charge, plus and minus, it can attract or it can repel. If you're calculating with Coulomb's law and you get a negative force, that indicates attract. and then a positive force indicates repel because of the way the math works out. So those are the two main comparisons between them. They are both, again, two of the four fundamental forces of nature, the strong force of the nucleus and the weak force in the nucleus being the other two. And that's it for Coulomb's law. Next we'll be looking at the inverse square nature and practicing the effects of changing these various values.